Okay, seems like everything's good. So today I want to look at, let's forget about interpolation for a moment. This one is, I think interpolation is pretty easy once you get the basic formula. And you probably won't need to do like very high order interpolation, so because what happens is that even so, if you have like 200 points, you might say, well, it's crazy, I'm not going to fit the parabola to these 200 points. It could be any kind of curve. But what you will actually be doing more realistically is you're not going to fit the polynomial of order 1 or of degree 199, because that would just be crazy. You can try it and you'll see that the polynomial goes through all the points, and yet between points it behaves like crazy. It just goes up through the roof and then down through the floor, and it's just crazy. The behavior outside of the points is completely unrealistic. And so instead of doing that, what you will be doing probably is to just locally approximate things by a polynomial. For example, polynomial of degree 3. Okay, that's a popular thing. So you have a polynomial of degree 3 locally, and then you impose some continuity condition because you have 200 points, right? So you fit a third order polynomial, which means you have 4 coefficients you can tweak. And just imagine for every 2 points you can fit a 3-degree polynomial, which means for it to go through these 2 points, you have to kind of have 2 equations on the coefficients, right? You have 4 coefficients on a 3-degree polynomial, 2 equations, so you get 2 free coefficients, if you will, and then you use that freedom to impose that the local approximations join at every intersection. So the complete function, which is a whole bunch of local approximations with a small order polynomial, is actually continuous. And then you also ask that the first derivative is continuous. And you can do that. You see the basic idea. And so then that's usually called the cubic spline. Cubic because it's a third order polynomial, and spline because it's it will behave a little bit like there are these rulers for drawing that are kind of curvy, but they are hard to bend sharply, so they make very smooth curves. And if you look at the physics of the material, it's at least in some approximation doing a similar thing of keeping, minimizing the first derivatives and so on. And that's called, I think, that's where the name comes from. Okay, so interpolation should be good, and we're not going to use it much for a relatively long time, and we're almost out of numerical methods to show you until we have enough to do a a lot of physics, but I think this section would be incomplete um, without showing you a more realistic example, because now you have like the toyish version of various kinds of numerical methods, and the reason I did it this way was so that the learning curve initially was kind of easy to bear, and you could get all of the other things that you need to get, like the computer language, dealing with the computer, experimenting on your own with the things, seeing how it can change stuff, and so if the content is simple, you can more efficiently go through that, I think. At least that was the theory. And then, so now let's just go through a more realistic example. I've shown you how you would do polynomials, and aside from certain certain considerations relating to memory usage and speed, those are perfectly valid polynomials that you can use, and the changes that you would have to make to put them into a system and have them be like rock solid and never have to worry about their performance characteristics are actually pretty easy and pretty kind of independent of the content of polynomials. So I might go through that later, but it's kind of boring for now because there's no use for it, and yeah, I think that's enough reasons not to go through with it. So now, but we will use the polynomials to do better integration. So how will that work? Well, if you remember, what's the, I think it's, yeah, okay. So for integration, the basic idea was that if you split the integral in small integrals, then you can approximate the function by a simple polynomial, like a constant or linear function or a parabola, etc. And since you can integrate polynomials exactly, then you have a formula which is going to be approximate when you're just approximating the function with a polynomial. And of course, the reason that works is that you can define a polynomial just by looking at the function on specific points. So you look at the function a few times, and then you take a polynomial that goes through all of these points, and you integrate it exactly, and you can do the formula for 2 points, 3 points, so you get higher order polynomials, or higher degree polynomials, and you get better approximations. But because of what we discussed a while ago about the limitations of how numbers are represented on a computer, it's not, the precision won't go up forever. The precision goes up when the error is dominated by how crude your approximation is, and then you hit a level where you did too many arithmetic operations, so that now the error is dominated by the numerical errors of working with numbers on a computer. And after that, it gets worse and worse. So even though you're doing more computation, even though your code is uglier, harder to manage, harder to understand, longer, more complex, even though it takes longer to run, your results are worse. Okay, because of that arithmetic error accumulated. There's also the fact that it's going to be pretty complicated. Okay, so can we do better? Do we have to just keep increasing the degree of the polynomial? Well, actually no, because if you just ask, okay, so we're going to be in the business of approximating the function by a polynomial and then integrating it exactly, integrating that approximation exactly, then you can say, well, what's the theoretical limit to that process? If you look at the function in n different points, okay, so instead of splitting the integral into lots of small integrals, just think of the whole integral, right? If you have, say, 1,000 points, right? You have 1,000 points. Well, you can approximate the function by a polynomial of degree 999, then use all of these 1,000 points to fit the polynomial, kind of adjust the coefficients. Okay, so the limit seems to be the number of points, but actually you can do better because you're allowed to choose the values on which you evaluate the function. You know, maybe the function comes from somewhere else, like an experimental result that you don't have any control over. But if you have some control over the source of the function, even though you might have it in the form that is like just a series of values, you can go back to the previous step in how the function is computed and use so adjust where you look at it. If you're in control of the process of computing the function, right? So for instance, if you have a function pointer like this, which means you know the address of a piece of code that computes the function, then you can just feed it any x value that you want, and you're going to get the value at that of f at that point. And because you have that freedom to choose, let's say, 1,000 values for x, then it turns out that the number, the degree of the polynomial that you can actually fit is 2n minus 1. And then you can integrate that exactly. So there's going to be a little bit of black magic, just because if you're really interested in that stuff, I think you should look it up yourself and try to figure it out. I think that would actually be valuable, I think. And also, if you're not interested in that, you can. It also shows you that sometimes, as long as you know what you want in numerical methods, it's